Okay, so let's start. So I'll start with basics of multivariable calculus. So first of all, what is the derivative of a map between, well, Euclidean spaces, more generally non-linear spaces? So uh, so first some preliminaries. So suppose E and F are non-linear spaces and T is a linear map from E to F. So then you define the operator norm of T by norm T is defined to be uh, the SOAP over V non-zero of norm TV by norm V. And this, you can take this norm V inside the norm here. So this becomes norm of T of V over norm V, which is T of a unit vector. So as V ranges over non-zero vectors, V over norm V ranges over unit vectors. So this supremum is the same as the supremum over the unit sphere of norm TV. And so geometrically, what is this? If, for example, T is a linear map from Rn to Rn, where Rn has the usual L2 norm, okay, then the image of the unit sphere under T, if T is invertible, suppose T is invertible, then this is an ellipsoid, the image of the unit sphere. And this SOAP of norm TV will be the major axis of the ellipsoid, right? So this length is norm T, norm T. Okay. So, I mean, how can you calculate this norm? It's quite easy. You look at norm T squared. So that's the SOAP over norm V equal to 1 of norm TV squared. So norm TV squared is inner product TV TV. So that's the same as inner product of T star T VV. And now T star T is a positive definite symmetric matrix. This is a quadratic form. So we can diagonalize this, right? So if we diagonalize T star T with respect to an orthonormal basis EI, so this is equal to, say, lambda I EI. So you have an orthonormal basis of eigenvectors, and then you arrange the eigenvectors in increasing order, the eigenvalues, sorry. So lambda n is the largest eigenvalue. And then if I write V as summation xi ei with respect to this basis, then this quadratic form just becomes, so then this becomes the SOAP over summation xi squared equal to 1 of summation lambda I xi squared, right? And so since summation xi squared is 1, this sum, this is less than or equal to lambda n into summation xi squared, which is lambda n. And you have equality. This is equal to lambda n if v is equal to en. Right? So this supremum is nothing but lambda n. Okay? So that means that norm t is it's a singular value of t, right? It's the largest singular value. So this is the largest eigenvalue of t star t to the power half. Okay, so that is what this norm is in terms of linear algebra, and geometrically it's just the major axis of the ellipsoid, which is the image of the unit sphere under T. Okay. And if you look at this definition, it's the sup of norm TV by norm V. So it's the largest stretching, right? You're looking at how much T stretches vectors, the length of the image divided by length of the vector in the domain. So this is the largest stretching of T. Okay, so some easy properties. So if I look at any vector V, then norm TV, if V is non-zero, I can write this as norm TV over norm V into norm V. And so this is less than or equal to, this term in brackets is less than the sup, which is norm T. So this is less than norm T into norm V. Okay. And if I have a composition of operators, so say T, so from say E1 to E2 and S from E2 to E3, then norm of S compose T of some vector V. If I apply the above inequality twice, this is less than or equal to norm S into norm TV, which is less than or equal to norm S, norm T, norm V. And so dividing by norm V and taking the supremum over V, non-zero, we get that the norm of ST is less than or equal to norm S, norm T. And so we have these two important properties of the operator norm. And then we can define the space of bounded linear maps from E to F, so that my notation will be LEF for this. This is defined to be linear maps from E to F such that norm T is finite. So this is a vector space, and it's a normed linear space, so with the operator norm. So this is a normed linear space. So in finite dimensions, we know that any linear map will be continuous So in finite dimensions, there's no distinction. So just to see that, I mean, let me recall that, any two norms on a finite dimensional space are equivalent. And so this is easy to prove. I mean, so you take your vector space E to be without loss of generality Rn, and then you're given some norm. So the first thing is, if I take the norm of a vector V, so V I write with respect to the standard basis as summation xi ei. Then by the triangle inequality, this is less than or equal to some mod xi norm ei. And so there are just finitely many EIs here. So I take the maximum of the norms of the EIs. So I call that some constant m. So then this will be less than m times the sum mod xi, which is the L1 norm of x. So the L1 norm of V. Yeah. So this norm is less than a constant times the L1 norm. And you want an inequality in the other direction. So for that, this inequality will tell you that the norm is a continuous function on Rn, because norm of V minus W, this is a continuous function because norm V minus norm W, the absolute value of this is less than or equal to norm V minus W, which is less than or equal to a constant times the L1 norm of V minus W. And this tends to 0 as V tends to W in Rn. So that means norm is a continuous function. And so if I restrict it to the unit sphere, where the L1 norm is equal to 1, then on the unit sphere, the norm is non-zero and it's continuous, and the unit sphere is compact. So it's a continuous function on a compact space. It attains its supremum and infimum, which are positive. And so that means that norm V is, so this shouldn't be C, this should be M, sorry. So this is less than its supremum, say, which is C, and bigger than 1 over C on this unit sphere by compactness. And then by homogeneity, norm V divided by the L1 norm of V will be bounded by 1 over C and C for all V non-zero. So is this okay?
Yes.
All right. So any two norms on a finite dimensional space are equivalent. And from that, you get that if E finite dimensional, then any linear map to any norm-linear space F is bounded because I mean, you can just take E to be Rn, and then the norm of T V. Again, you write V in terms of the basis as summation xi ei. So this will be less than or equal to bilinearity and the triangle inequality. So mod xi norm T of ei. And again, there are just finitely many norm Ti's, so I take the maximum of them. So this will be less than a constant m times the L1 norm of B. Okay. All right. So for finite dimensional spaces, we don't have to worry about this. But I just thought it would be good to give the definition of derivative for general nonlinear spaces. Okay, so now let's come to the derivative. So let me just recall quickly. So if I take a function from R to R, right, then the derivative, of course, you can think of as a real number, the slope of the tangent line. So this is x. This is f of x. And this slope is f prime x. But we can also think about this tangent line itself. So if I take a variable h, which is near 0, and I look at points x plus h, then what this tangent line does is it's the straight line which best approximates the graph of f near x. So what that means is, if I take a point on the graph here, so if I zoom in, then this tangent line gives me a linear function of h, which is the best approximation to f near x. So what that means is, here's the point on the tangent line, and here's the point on the graph, and this distance is h, and this is this distance, this is h times f prime x. And here, this is the error between the linear function and the actual function. This error will be small compared to h. So this is an error E of h, which is little o of h. Okay. So up to first order, the tangent line gives me the linear function which best approximates my function. Right? So I have a first order Taylor approximation. F of x plus h is fx plus a linear function of h into f prime x, plus an error term which is little o of h. Okay. So the idea to define the derivative in general will be to say that we have a best linear approximation to the function near a point. Okay, so I mean, so for example, if f was a function from, so here f was from R to R. And I mean, the derivative we were defining, normally you define as a limit h tends to 0, fx plus h minus fx over h. So this is a real number. But if I go to higher dimensions, so say f is from R2 to R, so then h is my change in x h is a vector in R2, so I can't divide by h anymore. Instead, I try and copy this picture. So I look at the graph of f. So that will be some surface. Okay. So maybe this is the graph of f. And then I take a point on the graph. And then I look at the tangent plane to this, right? So the tangent plane will be the graph of a linear function of h. And that linear function, like in this picture, will give me the best approximation to f. So here's my point on the tangent plane, and here's the point on the graph of f. And again, what I want is, the error in the approximation. This error here should be small compared to h. So the general definition is the following, that if I have f, which is a map from an open subset of a norm-linear space E to a norm-linear space F, then we say it's differentiable at a point x0 in U if there exists a bounded linear map T in LEF such that we have a first-order Taylor approximation near x0. F of x0 plus h is fx0 plus th plus E of h, an error term where E of h is little o of h as h tends to 0. So h is a vector. So what does this mean? This means that the norm of EH divided by the norm of h tends to 0 as h tends to 0. So this is the definition of differentiability. And so in this case, you can see that if I take a line passing through x0 in the direction of a vector h, then if I restrict f to that line in the direction of h, so the line will be points of the form x0 plus th, where t is a real number. Then f restricted to this line gives me a map from an interval into a vector space. So it gives me a curve in the vector space f. So for this curve, I can look at its tangent vector. Right? That will be the limit t goes to 0, f of x0 plus th minus fx0 divided by t. So this is called the directional derivative of f in the direction h at the point x0. So it's written nabla sub h of f at x0. And this limit, if we use this first order Taylor approximation, it's easy to see that this limit exists and equals t of h. Okay. If such a linear map t exists, then all of these directional derivatives will exist and equal the linear map t applied to the vector h. So in particular, this tells me that if f is differentiable at a point, that is, if such a linear map exists, then it is unique because it's given by the directional derivative, right? And that doesn't depend on the linear map t. So this only depends on f. So this linear map T, if it exists, then it's unique. And then we define the derivative of f at the point x naught, df at x naught, to be this linear map T. So the derivative is a linear map from E to F. Okay. So, I mean, how do we reconcile this with the usual derivative of a map from R to R? So here what happens is the derivative, so for F from R to R, we have f prime x is a real number, and sorry, this seems to be stuck. Yeah, so f prime x is a real number, and df at x is a linear map from R to R. Okay. The point is that since R is a one-dimensional vector space, the vector space LRR of linear maps from R to R is isomorphic to R itself, right? And the isomorphism is just T maps to T of 1. Okay, this is an isomorphism. And under this isomorphism, if I take df at the point x, then this maps to dfx of 1. Okay? And see, what will the derivative as a linear map be? Dfx of h, you can see from this expression, it's going to be f prime x times h. And so dfx of 1 will just be f prime x. Okay. So under this isomorphism from LRR to R, the abstract derivative, the linear map dfx, is identified with the scalar, the real number f prime x. Okay, so that reconciles the two definitions of derivative. Okay. Okay, so let's quickly look at some examples. So for example, if I have a curve gamma from an interval in R into my normed vector space E, and suppose gamma is differentiable, then we define the tangent vector at a point, gamma prime t, to be the usual limit h tending to 0, gamma t plus h minus gamma t over h. And since gamma is differentiable, this is the same thing as d gamma t, d gamma at the point t applied to 1. Right? Remember that d gamma at the point t, this will be a linear map from R to E. So this applied to 1, this will be a vector in E. Okay? And the derivative d gamma t as a function of h is just h into d gamma t of 1 by linearity. And d gamma t of 1 is gamma prime t. So this is h into gamma prime t. All right. So now if I look at a map between Euclidean spaces, f from Rn to Rm. Okay. So first of all, we can define the partial derivatives of f, del f del xi at a point P. This is defined to be the directional derivative of f in the direction of the ith basis vector ei. So this is nabla sub ei of f at P. And as we saw earlier, this directional derivative is equal to the derivative applied to the vector. So this is dfp applied to ei. Okay. So this is a vector in Rm, okay, when f is differentiable. And this will give us an expression for the matrix of the linear map df So df at p is a linear map from Rn to Rm. So its matrix is an m by n matrix. So what is that m by n matrix? So if f, it's a map into Rm, it has coordinates f1 to fm, then the jth partial derivative, del f del xj, it's easy to see this is given by just taking the jth partial derivatives of each coordinate, del f1 del xj up to del fm del xj. And so then what will the matrix of dfp be? Well, the columns of the matrix are just the images of the basis vectors e1 to en under dfp, right? So the matrix will be dfp e1 up to dfp en, and dfp e1 is just del f del x1 at p, and dfp en is del f del xn at p. And these partial derivatives, del f del x1 up to del f del xn, these are the column vectors, del f1 del xn up to del fm del x1, and del f1 del xn up to del fm del xn. Okay, so we see that the matrix of the linear map df is just the usual Jacobian matrix of f, of partial derivatives, del fi del xj. Okay, all right. So now we have the chain rule. So if I have a composition of differentiable maps, say f going from a normed space E to a normed space capital F, and G going from a normed space capital F to a normed space capital G, then the chain rule says that the composition G composed F from E to G is differentiable, and it gives you a formula for the derivative. So the derivative of G composed F at P, so this is a linear map, this is equal to the composition of the linear maps dg at f of p composed with df at p. Okay, so intuitively what this is saying is that, see, df at p is the best linear approximation to f near p, and dg at f of p, this is the best linear approximation to g near f of p. And so it's natural to expect that the best linear approximation to G composed F would be given by composing the best linear approximations to G and F. Okay, and that's what the chain rule tells you. Okay. All right. So the derivative of a composition is the composition of the derivatives as linear maps. And one particular case of this is useful for us. If I look at a curve gamma inside my vector space E, and then I have a differentiable map F from E to capital F. So then if I look at the composition, F compose gamma, so by the chain rule, this will also be differentiable. And now, what will the tangent vector to F compose gamma be? So F compose gamma prime of T, this, as we saw above, this is the derivative d of F compose gamma at the point T applied to 1. And now by the chain rule, this is df at gamma T applied to d gamma at T applied to 1. And d gamma at T applied to 1 is nothing but gamma prime T. So this becomes df at gamma T applied to gamma prime T. Okay. In other words, what this is saying geometrically is that if this is your curve gamma, and so this is the tangent vector gamma prime T, and then I apply F to this, then I get some other curve, and so this will be F compose gamma prime T. Okay. And the chain rule is saying that df will map tangent vectors to gamma to tangent vectors to the curve F compose gamma. Okay, so this is equal to df at the point gamma t applied to gamma prime t. So the derivative maps tangent vectors of curves to tangent vectors of the image curves. Okay, so we have less than a minute. So let's end this meeting and start a new one. Okay, so I'll see you in a new meeting. Okay, so I'm stopping this now. Yeah, what's up? Okay, all right. Okay, okay. So, all right. Okay, so right. So the derivative maps tangent vectors of curves to tangent vectors of the image curves. Okay, so now we come to what's called C1 mappings. So, well, I've defined it for a map between Euclidean spaces. Okay, fine. So, so we'll say that a map F from Rn to Rn is C1 if the following holds. So suppose F is differentiable, right? So then I get a map dF which sends a point P in Rn to the linear map dF at P, right? So this gives me a map from an open subset in Rn to this vector space, this normed vector space, L of Rn comma Rm, right? So I'll say that F is C1 if this map is continuous. Okay, so this is a map between normed linear spaces, so I can talk about its continuity. So I'll say that F is C1 if this map is continuous, and then it's a theorem that F is C1 if and only if for all the partial derivatives del f del xi exist and are continuous. So one direction of this theorem is easy. If f is C1, then we know that the partial derivatives exist. And since the partial derivatives are just the columns of the matrix df, if df is a continuous function of p, then these columns del f del xi of p, these will be continuous functions of p, right? So one direction is easy. The non-trivial direction is the reverse implication that if all the partials exist and are continuous, then first of all, f is differentiable, and secondly, f is C1. Okay, so let me just emphasize the key point here is that the partial derivatives are continuous. Okay, because just existence of the partial derivatives doesn't imply differentiability of f. It's easy to give examples where the partials exist, but f is not differentiable. The point is the continuity of the partial derivatives that implies the differentiability of f. Okay? So that's the real content of this theorem. Okay. All right. So now let me recall the mean value theorem. So the mean value theorem for functions of one variable, it's an equality. Fx minus fy equal to f prime of some c into x minus y. But in higher dimensions, we can't expect an equality. Instead, the mean value theorem becomes an inequality. So if I have a function f on a open convex subset of Rn, taking values in Rm, and suppose f is C1, then the mean value theorem says the norm of fx minus fy, this is less than or equal to the sup over z in the line segment from x to y of the operator norm of df at z, this into norm x minus y. Okay. So geometrically, what does this mean value theorem mean? You see this quantity here, this norm of df at z, this is the, so I have an open convex set and I'm taking 2 points in them, x and y, and I'm joining them by a straight line in my convex set. And then if I look at the image of this line segment under f, that will be some curve joining fx to fy. Okay. And what I'm estimating is this straight line distance, right? Norm fx minus fy. Okay. So the estimate is that norm fx minus fy is less than or equal to the sup of norm df z over z in the interval xy into norm x minus y. Okay. And what is this quantity here? This norm dfz, this gives me the infinitesimal stretching near a point z on this line. How much f stretches vectors infinitesimally, right? And so you can imagine proving this as follows. Just the idea of this statement is you divide this line segment into very small, into a fine partition, right? And then you look at the image of the partition under F, right? So here, if I have a length h, then here in the image, this length would be bounded by norm df z into norm h, right? So now when I sum over the partitions, I'll get that norm fx minus norm fy, that's less than or equal to, by the triangle inequality, the sum of these lengths, right, between points in the partition. And each of these lengths is less than a length here, norm h, into norm of dfz, right? And so then this norm dfz, because f is c1, this is bounded on this compact interval from x to y. So I can bound this norm dfz by the supremum of norm dfz. And then when I sum over these norm h, I'll just get the length of the interval from x to y, which is norm x minus y. Okay, so does this make sense? Yeah. So, okay. Right, so this is the maximal infinitesimal stretching, this sup of norm dfz. And this, so if I rewrite this, then what it's saying is that norm of fx minus fy divided by norm x minus y is less than or equal to this, right? So sort of this is the global stretch factor. And this is the maximum infinitesimal stretch factor. Okay, makes sense. Yeah. So this is the mean value theorem. Okay? I mean, it may intuitively, I think it's should be intuitively clear, right? If say infinitesimally you can only stretch things by a factor of 2, then globally you should only be able to stretch by a factor of 2, right? So So that's the mean value theorem. Okay. So as a corollary of the mean value theorem, you see that if df is 0 everywhere, then f is constant, right? On this open convex set. And on a general open connected set, if df is 0 everywhere, then if you apply the mean value theorem to balls contained in this open set, which are convex, then you'll get that f is locally constant. And so therefore, because the set is connected, you'll get that f is constant on the whole set, on the whole open connected set. Okay. So a function whose derivative is 0 everywhere is constant on an open connected set. Okay. All right. So yeah, this also tells you that a C1 map is Lipschitz, right? This also tells you a C1 map is locally Lipschitz. Okay. So we'll say now, what is a C1 diffeomorphism? It's a map between open subsets of Rn, which is C1 and has a C1 inverse, G from V to U. Okay. So it's a C1 map with a C1 inverse. And now we can state the inverse function theorem. So this actually, in generality, this is true for Banach spaces. So if E and F are Banach spaces, and F is a map from an open subset of E to the vector space F, and F is C1, then if I take a point x0 in D, such that df at x0 from E to F is invertible, then there exist open neighborhoods U of x0 and V of fx0, such that F from U to V is a C1 diffeomorphism. So for a C1 mapping, if the derivative is an invertible linear map at some point, then in a neighborhood of the point, the map itself is invertible, right? So that's the inverse function theorem. And now let me recall the implicit function theorem. So this is for a map defined on a product space E cross F into G. So for such a map, I can define, so it's a function of two variables, one vector in E and another vector in F. So I can define partial derivatives with respect to the two variables in E and F, right? So the first partial derivative, d1f at a point x0, y0, this is defined to be the following. So I fix y equal to y0, and I consider capital F as just a function of x. So I have a function of x goes to f of x comma y0. So this is a function map from E to G. So I look at the derivative of this map at the point x0. So that will be a linear map from E to G. Okay. And the first partial derivative, d1f, is defined to be this linear map from E to G. Similarly, I can define the second partial derivative, d2f. That will be the derivative of the map y goes to f of x0 comma y. So I fix x equal to x0 and I just vary y. So this will be a linear map from F to G. And so I get these two partial derivatives. One is a linear map from E to G. The other is a linear map from F to G. And these I can write in terms of the total derivative. That will be a linear map from E cross F to G. And so the first partial, d1f of H, is nothing but df of H comma 0. And the second partial, d2f of a vector k, is df of 0 comma k. This is easy to see. So, all right, so now I can state the implicit function theorem. So if E, F, and G are Banach spaces, and F from an open subset D in E cross F to G is a C1 map, then if I take a point x0, y0 in D, such that the second partial D2F, so this is a linear map from F to G. So suppose this is invertible, then there are neighborhoods U containing x0 and V containing y0. And there is a unique C1 map, little g, from the neighborhood U to the neighborhood V, such that G of x0 is y0. And the set of points xy in D, such that f of xy is equal to f of x0, y0. In other words, a level set of f passing through the point x0, y0. If I look at this level set near the neighborhood U cross V of x0, y0, then in this neighborhood, this level set is equal to the graph of this C1 map G. So this is of the form x comma gx, x ranges over U. Okay, so let me just draw you the picture. So the picture is, here you have your Banach space E. Here you have your Banach space F. And here I have my map little f, which takes values in whatever G. And so this point is, say, C equal to f of x0, y0. And so here's the point x0, y0. And what I'm looking at is the level set f equal to C. Okay. And what the implicit function theorem is saying is that locally, if the partial derivative with respect to the y variable is non-zero, is invertible, then this level set will be the graph. So I'll have a neighborhood U here of x0 and a neighborhood V of y0, such that in this product neighborhood, this is U cross V, this will be equal to a graph. So if this point is x, so then this will be of the form x comma g of x. Okay. So that means restricted to the level set, y becomes a function, y equal to g of x, a function of x on this level set. Yeah. Oh, all right. So I just wanted to recall some basics of the basic theorems, the inverse function theorem and implicit function theorem. We won't really be using them, but I just wanted to recall them for completeness. So what we will be needing a bit more is what are the higher derivatives now? Okay, so what are higher derivatives? So to talk about higher derivatives of a map between Euclidean spaces, we need to talk about multilinear maps. Okay. So suppose E and F are norm-linear spaces, and T is a multilinear map of k vectors from E cross E cross E k times to F. Then we can define the norm of this multilinear map similar to how we define the norm of a linear map. So the norm of T will be defined to be the sup over vectors v1 to vk, which are of norm 1. So norm v1 equal to 1 up to norm vk equal to 1. And then you take the sup of norm of T of v1 to vk. Okay. So we'll say that a multilinear map is bounded if this supremum is finite. Again, in finite dimensions, this is easy to show this is finite. But this norm is useful because like the operator norm of a linear map, this norm of a multilinear map, it satisfies this property, that by definition, the norm of T of V1 to Vk is less than or equal to norm T into norm V1 up to norm Vk. All right. And so then we define MKEF to be the set of multilinear maps T from E cross E cross E k times to F, whose norm is finite. Again, in finite dimensions, this is just all multilinear maps from E to F, E cross E k times to F. Okay. All right, so why are we interested in multilinear maps? Because these arise when you consider higher derivatives of a map between vector spaces. So suppose F is a map between normed vector spaces E and F, which is differentiable. So then we'll say it is twice differentiable if the following holds. So you look at DF now. So DF is the map which sends a point P in E to the linear map DF at P. So this is a map between normed vector spaces, right? From E to LEF. So I can ask, so it's again a map between normed vector spaces. So I can ask whether this map is differentiable, right? So then I will say that F is twice differentiable if this map is differentiable, the map which sends P to DF at P. Okay. So in that case, the second derivative of F at P is defined to be the derivative of this map DF at the point P. So DF is a map from open subset of E to the vector space LEF. So its derivative is going to be a linear map from E to the vector space LEF, right? So by definition, the second derivative, d squared F at P, this is a linear map from E to L of EF, right? Okay. Now, what is this space? Linear maps from E to L of EF. Well, this can be naturally identified with bilinear maps from E cross E to F. So the isomorphism is an element on the left-hand side T here. This will give me a bilinear map T hat. So how is T hat defined? T hat of two vectors V1, V2 in E is the following. So you take T first and apply it to V1, right? So what does T do? It's a linear map from E to the vector space LEF. So given a vector V1 in E, T of V1 is an element of LEF. All right, so this TV1 is an element of LEF. Therefore, it can act on another vector, V2, right? So TV1 will act on V2, and that will give me a vector in F. Okay, so this will give me, therefore, a bilinear function of V1 and V2, right? Okay, so this is just some abstract nonsense. It's nothing difficult, yeah? So what we see is that this map, in fact, T goes to T hat. This will be an isomorphism. And in fact, it will be an isometric isomorphism. So the operator norm here will be of T will be the same as the norm of T hat as a bilinear map. Okay, this norm which I've defined here. Okay, this is easy to see. Okay, so this second derivative, therefore, is naturally identified with a bilinear map from E cross E to F. Is this okay? So,
Yes.
So how do we calculate this second derivative? Let's do some calculations. So first of all, notice that suppose I have a differentiable curve, T maps to A sub T in the vector space LEF. Then if I take a vector V and I apply AT to V, V is a vector in E. Then if I look at the tangent, so this gives me a curve in F. So then ddt of ATV, this is easy to see. This is equal to ddt of AT, okay, the whole thing applied to V. Right? So AT is a curve in LEF. So ddt of AT, this will be an element of LEF. So I can apply it to the vector V. All right. So this is easy to show. And now suppose I have F, which is a twice differentiable map from E to F. Let's look at, let's take two vectors V and W, and let's look at the following. I look at DF at the point P plus TV, and I apply it to W, okay? And then I want to differentiate. So this gives me a curve inside capital F, right? Inside this vector space capital F. So I want to differentiate this at time t equal to 0, okay? I take ddt at t equal to 0 of this. So by this earlier property here, so since f is twice differentiable, that means df as a function of p is differentiable. So in particular, df along a straight line p plus tv, this will be a differentiable curve in the space LEF. So by this property here, this ddt at t equal to 0 of df of p plus tv of w, this will be the same as ddt at t equal to 0 of df at p plus tv, the whole thing applied to w. Now, what is ddt at t equal to 0 of df at p plus tv? By definition, this is the second derivative, d squared f at p applied to the vector v, right? Yes, is that okay?
Yes.
Right. So what do I get? I get d squared f at p applied to v, and then that applied to w, right? So this is exactly d squared f at p applied to vw when viewed as a bilinear map, right? So I can calculate this bilinear map in this way, that d squared f at p applied to a pair of vectors v and w is nothing but ddt at t equal to 0 of df at p plus tv applied to w. Okay. And if I take w equal to v, then what happens? So if I take the second derivative, d squared dt squared at t equal to 0 of f of p plus tv. Okay, so let me take the second derivative of this curve, f of p plus tv. Then when I differentiate once, by the chain rule, this is going to be df at the point p plus tv applied to the tangent vector to this straight line is just the vector v, right? So this will be df at p plus tv applied to v. And then I'm taking ddt at t equal to 0. So by the previous line, this will be d squared f at p applied to v comma v, right? Okay. So so you see this d squared f at p applied to v comma v. I mean, if f was a real valued function, then since this is a bilinear function applied to v comma v, then this will be a quadratic form in v, right? This will be a quadratic form in v. And this quadratic form I can get by taking the second derivative of f along a straight line passing through p in the direction v. Okay. Okay, so taking the second derivative gives me a quadratic form in the vector v. Is this all right?
Yes.
Okay. All right. Okay. So exactly. So now let's come to f from Rn to R, concrete example. So in this case, let's look at the a second partial derivative, del squared f, del xi, del xj. Okay, applied to p. So what is this? This is del xi of del f del xj, right? So by definition, this is d dt at t equal to 0 of del f del xj applied to p plus ti, right? Now, what is del f del xj of p plus ti? Remember, del f del xj is just the derivative df at this point applied to the vector ej, right? So this will become d dt at t equal to 0 of df at p plus ti applied to ej, right? Now this, by the calculations that we've done above, this is nothing but d squared f of ei comma ej, okay? D squared f at the point p, there's a p missing here. So this is d squared f at p applied to ei comma ej. Okay. So these second order partial derivatives are nothing but d squared f at p applied to ei comma ej. Is this clear? Yeah. Okay. All right. And okay, so we will, in this course, we'll be needing the second derivative. We won't be needing higher derivatives. But let me just say what happens for higher derivatives. So in general, so you put the higher derivatives, you define the spaces where they live inductively. So you put L1 of EF to be LEF. Okay. Then you put LK of EF to be L of E comma LK minus 1 EF. All right. So these are spaces defined inductively for k greater than or equal to 2. And then it's easy to see that LK of EF, this is isometrically isomorphic to MK of EF, where MK of EF is the space of k multilinear maps from E, bounded k multilinear maps from E to F. Okay. So now we'll say that F, little f from open subset U in E to capital F is k times differentiable if little f is k minus 1 times differentiable, and if I look at the k minus 1th derivative, dk minus 1f. So this, by definition, is a map from U into the space lk minus 1 ef, which sends p goes to dk minus 1 f at p. If this map is differentiable, then we'll say that f is k times differentiable. And so then dkf at p, the kth derivative is what? It's the derivative of this map, dk minus 1f. So d of dk minus 1f at the point p. So this will be a linear map from where to where? From E to the vector space lk minus 1 ef, right? And so that means that dkf at p, this is an element of the vector space linear maps from E to lk minus 1 ef. And this, by definition, is what we're calling lk of ef. And this is naturally isomorphic to mkef. All right, so the kth derivative is naturally identified with a k multilinear map from E cross E cross E, k times to f. Is this okay? Does this make sense?
Yes.
Okay, so the kth derivative is a k multilinear map at each point. All right. And so again, if I take a function from Rn to R, which is k times differentiable, then like we saw here, the second order partial derivatives were given by the second derivative applied to the basis vectors ei, ej. Similarly, for higher derivatives, a kth order partial derivative, del kf del xi1 up to del xik, this is equal, one can show, it's not hard to show, this is equal to the kth derivative dkf at p applied to the vectors ei1 up to eik. Okay, where ei is the usual standard basis of Rn. All right. So now we can talk about what is a CK map. So F, a map between Euclidean spaces, is CK if F is K times differentiable and this DKF, which is the map which sends P to DKF at P. So this is a map from Rn to the space of K multilinear maps from Rn to Rm. This should be an N here. There's a typo. Sorry. So we'd say that F is CK if F is K times differentiable, and this map P goes to DKF at P. This is continuous. Okay. And then it's a theorem. So this is similar to the theorem we stated for C1 mappings. So similarly, you can prove, in fact, using that theorem for C1 mappings, you can prove by induction that F is CK if and only if all partials of order less than or equal to K exist and are continuous. Okay. So this is a theorem. Again, one direction is easy, that if F is CK, then all the partials of order less than or equal to K will exist and be continuous. It's the converse which is the non-trivial part. All right, that if all the partials of order less than or equal to K exist and are continuous, then this DKF at P exists as a K multilinear map at each point, and P goes to DKF at P is a continuous map. Okay. Is this all right? So, okay. And then F is C infinity if F is CK for all K. Okay. So this will be if and only if all partials of all orders exist and are continuous. Okay. So, I mean, this is normally, I mean, this right-hand side is what is given as the definition of C infinity usually, but well, I just wanted to actually make the point that genuinely the definition really should be in terms of these higher derivatives as multilinear maps. All right. So, okay. You see, the information of all the partial derivatives is contained in these multilinear maps, right? This multilinear map contains all the information of the partial derivatives. The partial derivatives are just given by applying the multilinear map to the basis vectors. All right. Okay. Is this okay? Yeah.
Fine.
Okay. Fine. All right. So now we say that if UV are open subsets of Rn and F is, then we say that F from U to V is a C infinity diffeomorphism if F is C infinity and has a C infinity inverse, G from V to U. Okay. All right. So now let me come to Taylor's theorem. So like we saw here above, we saw that this second derivative along the diagonal applied to V cross V, V comma V, this is equal to the second derivative of F along the straight line in the direction of V. Similarly, it's not hard to show that the kth derivative applied to V comma V comma V K times is equal to the kth derivative at t equal to 0 of F of P plus TV. Okay. All right, there's less than a minute. Let me stop this and we'll start another meeting. Okay. 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 So, all right. Okay. So, right. So here the kth derivative is a multilinear function from Rn cross Rn K times to R, and applied to a vector, applied to along the diagonal, applied to V comma V comma V K times. It's nothing but the kth derivative of the curve F of P plus TV. Well, this is a function of one variable, actually, if f is real valued. Okay. So we have the following Taylor's theorem, that if f is a CK map from an open subset in Rn to Rm, and I take a ball of radius r around a point x, which is contained in my domain U, then for norm h less than r, for points in this ball, f of x plus h is fx plus dfx applied to h plus 1 over 2 factorial d squared f at x applied to h comma h plus 1 over 3 factorial d cubed f at x applied to h comma h comma h, and so on, up to 1 over k factorial dk f at x applied to h comma h comma h, plus a remainder term rk of x comma h. Okay, where this remainder, we have an explicit integral formula for the remainder. It's 1 over k minus 1 factorial, integral from 0 to 1 minus t to the power k minus 1, in brackets, dkf at the point x plus th applied to h comma h comma h, minus dkf at the point x applied to h comma h comma h, whole thing integral dt. Okay. So notice, if f is ck, then dkf as a function of x is a continuous function. So when h tends to 0, when norm h tends to 0, dkf at the point x plus th is close to dkf at the point x, right? So the difference between the norm of the difference between these two multilinear functions is tending to 0 as h tends to 0. And so applied to h comma h comma h, we have that this difference will be less than the norm of the difference into norm h power k, right? So I'm using this this property of the norm of multilinear functions, that norm of t of v1 to vk is less than or equal to norm t into norm v1 up to norm vk. So if I take v1 up to vk equal to h comma h comma h, then norm of t of h comma h comma h is less than or equal to norm t into norm h power k, right? So that's what I'm using here in this Taylor, in this remainder term. The norm of dkf x plus th minus dkf x, the norm of that multilinear function is small, and then applied to h comma h comma h. So therefore, that will be less than that norm into norm h power k. So the whole thing will be something small into norm h power k. So this is little o of norm h power k. All right. So what we get is that these terms you see, this dfxh, this is a linear polynomial in h. D squared fx of hh, this is a homogeneous quadratic polynomial in h. This d cubed fx of hhh, this is a homogeneous cubic polynomial in h. And this last term is a homogeneous kth degree polynomial in h, right? And the remainder is little o of norm h to the k. Okay. So, I mean, this Taylor formula, this Taylor polynomial, I mean, to see it as a polynomial, it's the usual, you see, this I mean, I can write this in terms of partial derivatives if you want. So in terms of partial derivatives, what happens? So this, let's look at, say, for example, the kth term, 1 over k factorial dkfx h h. Plus there's the remainder term. So I'll just write that as little o of norm h to the k. So this term here, this I can expand out using multilinearity, right? If I write h is equal to summation hi ei, right? Then by multilinearity, this will become a sum over k indices, sum I1 up to ik, right? Then by multilinearity, I'll get dkf x of ei1 eik into hi1 up to hik, right? And this dkfx of ei1 to eik, this is the same as the partial derivative del kf del xi1 del xik, right? The whole thing at the point x. Is this clear? So this gives the usual Taylor expansion in terms of polynomials where the coefficients are the partial derivatives. Is this clear?
Yes.
Yes.
Okay. This hi1 to hik, this is gives you homogeneous polynomial of degree k, right? In H. Okay. So, okay. All right. So, good. So we have this Taylor's theorem, and okay. Okay, so now we just do some linear algebra, just some linear algebra. So suppose V is a finite dimensional real vector space, and EI is a basis of V, and EI star is a dual basis of V star. Okay. Then we define V star tensor power k to be the space of k multilinear functions from V to R. Okay. Actually, there's an abstract definition of the tensor product, right? In terms of a universal property, or you can write it as some free vector space quotiented by some relations. There's an abstract definition of a tensor product. But when I take the dual of a vector space, a finite dimensional vector space, then the tensor products of the dual are canonically isomorphic to multilinear functions from V to R, all right? So actually there's some isomorphism here, but I'm defining this V star tensor K to be MKVR, all right? Is this okay? Yeah. I don't know if you've seen the abstract definition of the tensor product in your algebra courses, right? You've probably seen it in algebra.
Yes.
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 So for V star tensor powers, they turn out to be multilinear functions on V, okay? So there's some isomorphism here actually. All right, a natural isomorphism. Okay, now so what is the tensor product of two elements of these tensor powers? So if alpha belongs to V star tensor power K and beta belongs to V star tensor power L, that means alpha is a K multilinear function on V and beta is a an L multilinear function on V. Then alpha tensor beta, this is a K plus L multilinear function on V, which the definition is very simple. Alpha tensor beta acting on K plus L vectors, V1 to Vk, W1 to WL, is nothing but the product alpha acting on V1 to Vk times beta acting on W1 to WL. Okay. So this is easy to see. This is multilinear in each of the vectors Vi's and Wi's, right? So this is a K plus L multilinear function. And now I can take repeated tensor products. So if I take my dual basis, EI stars, then these are linear functions from V to R. So I can, if I take tensor products of them, if I take tensor products of K of them, EI1 star tensor EIK star, then this will be a K multilinear function. And it turns out as I1 to IK range over the set 1 to N, these tensor products will give me a basis of the space V star tensor K. In other words, this is a basis of the space of all K multilinear maps. Okay. And in fact, if alpha is a K multilinear function, then alpha I can write explicitly as a sum over I1 to IK ranging from 1 to N, alpha of EI1 up to EIK into EI1 star tensor EIK star. Okay. So the coefficient of alpha with respect to this basis is nothing but alpha of EI1 to EIK. So this is not hard to show. All you have to show is that, I mean, the left-hand side and the right-hand side, these are both multilinear functions which take the same value when applied to a K tuple of the basis vectors, say Ej1 up to Ejk. Okay, so if they take the same values on K tuples of basis vectors, then they, by multilinearity, they're equal. Okay, so this is not hard to show. Now we want to apply this to the kth derivative of a K times differentiable map from Rn to R. So in this case, dkf at P, this is a K multilinear function on Rn. So it's an element of Rn star tensor K. Okay. And so by this above formula, I can write dkf at P as a sum over indices I1 to IK, dkf at P applied to EI1 to EIK into EI1 star tensor EIK star. And this dkf at P applied to EI1 to EIK, as we've already seen, this is equal to the kth partial derivative, del kf, del xi1 to del xik at P into EI1 star tensor EIK star. Okay. So we have an explicit expression for the kth derivative in terms of the partial derivatives. All right. Okay, so the partial derivatives, you can think of them as coefficients of this K multilinear map with respect to this standard basis of the space of K multilinear maps, multilinear functions. Okay. Okay, so now let me recall for you that we have equality of mixed partial derivatives, right? So if f is a ck function where k is at least 2, and then for any L less than or equal to k, if I take a permutation sigma in SL of L symbols, then any Lth order mixed partial derivative, this is invariant under permutation, right? So del LF of del xi1 up to del xil is the same as del LF of del xi sigma 1 up to del xi sigma L. Okay. So this is a standard theorem. So using this, we can show that the kth partial derivative, sorry, the kth derivative is a symmetric multilinear map. So So what I mean is the following. So suppose I take say V1 to Vk in Rn, and I take sigma is a permutation of k symbols, sigma in Sk. Okay. And so let A be the set 1 up to n. Okay. And let me call, say, I bar to be a multi-index, I1 up to Ik in A power k. Okay. So the symmetric group acts on A power k, right, by permutations. Right, sigma dot I1 to Ik is, well, maybe the action should be from the right, not from the left. Okay, fine. So if I want it to be action, probably I should act from the right, I think. Yeah. So I1 to Ik dot sigma equal to I sigma 1 up to I sigma k, right? This is the action. Yes. Okay. So now if I look at the kth derivative dkf at p applied to v1 to vk, this is equal to the sum over I bar element of A power k del k f del x I1 del x Ik at p into v I1 1 up to v Ik k, where Vj I write as a column vector, V1j up to Vnj. Right, we have this formula. Yes, this is okay. Yeah. So now I apply, basically, I make a change of variables. I put, I replace I bar by sigma dot, well, I bar dot sigma. Okay. So that will just permute the sum, right? So this is the same as a sum over I bar in A power k del kf del x I sigma 1 del x I sigma k v I sigma 1 1 up to v I sigma k k, right? Now, this product here, if I look at this product here, V I sigma 1, 1 up to, so I'll get some Vi, the general term will be sigma J, J, Vi sigma K, K, right? So here, sigma 1 up to sigma K will just be a permutation of 1 to K, right? Sigma 1 up to sigma K is just a permutation of 1 to K. So, so when sigma J is equal to 1, let's say, then that means that J is equal to sigma inverse 1, right? So that means this term here will become Vi1 sigma inverse 1, right? So this whole product therefore will become Vi1 sigma inverse 1 up to Vik sigma inverse K, right? Yes. And so therefore this sum becomes sum over I bar in A power K. And now I use the equality of mixed partial derivatives. So this mixed partial derivative is invariant under permutation. So this is the same as del Kf. So there's a P here. Del Kf del x I1 del x Ik at P into Vi1 sigma inverse 1 up to Vik sigma inverse K. Right? Is this okay?
Yes.
Okay. And this, you can see, this is nothing but the kth derivative dkf at P applied to V sigma inverse 1 up to V sigma inverse K, right? Yes?
Yes.
Right? So what does that tell me? That tells me that the kth derivative as a multilinear function, it is invariant under permutations, right? It is invariant under permutation. So this is true for all sigma in Sk, right? Okay, so that means that dkf at P is actually a symmetric multilinear map. Okay, so which means by definition it is invariant under permutation of the K vectors that it's acting on. Okay, so it's a symmetric multilinear map. Okay, so the kth derivatives are actually symmetric multilinear maps. And for a symmetric multilinear map, one can show that if T, so if this is a symmetric multilinear map from say Rn to R, okay, then T is determined by its values along the diagonal. That means if T of V comma V is 0 for all V in Rn, then T of V1 up to Vk is 0 for all V1 to Vk in Rn. So any idea how to prove this? So for k equal to 2, I guess you know what to do, right? If it's a symmetric bilinear function, then you can just use the polarization identity, right? The parallelogram identity, right? Like you do for the inner product, yes?
Yes.
But what do you do for higher k? So if k is 3 or 4 or higher, any idea how to prove this? Okay, so actually the proof is the following. You look at the function f of x, which is t of x comma x. So this is a polynomial function of degree k, right, in x. It's a homogeneous polynomial of degree k, right? And so this will be C infinity, right? It's just a polynomial function. What are the derivatives of this? Well, it turns out, I mean, the first derivative is easy to see what the first derivative will be. dfx of h will be k times t of 1h and k minus 1 x's, right?
Yes.
Okay. Now you calculate by induction the higher derivatives, and what you will find, I leave it to you as an exercise, is that dkf at x. So this will be a multilinear function, right? Of h1 up to hk. This is a multilinear function. This is nothing but, what do you think this will be? Any guess? Any guess? Orkojit?
K factorial t
Oh, very good. Yes.
K fact into t. I guess all.
Yeah, you're right. Yeah, it's k factorial into t itself of h1 to
Right,
hk.
right. Because all the coordinates will be filled here.
Right, right. That's it. That's it. Okay, so this proves it, right? So if t is 0 along the diagonal, then f is 0, and so its kth derivative is also 0. Therefore, t is 0. Is this clear?
Yes.
Okay. All right. So this means, in particular, for example, that if I have a function in Rn such that along any straight line through a point P, the kth derivatives are 0. So suppose dk ddtk at t equal to 0 of f of p plus tv, if this is 0 for all v, okay, now what is this kth derivative of this along this line? This we know is equal to dk f p of v comma v, right? For all v in Rn. Then we know now from the above that dkf at p is identically 0. And this implies that all kth order partials del kf up to del xi1 del xik at P are 0, right? For all I1 to Ik. Okay, is this clear?
Yes, sir.
Yes.
So, Rudrada, I think this is what I was trying to say the other day when we were talking. I think. So,
Yeah.
anyway, this is what I was saying. So, yeah, so if the kth derivatives along straight lines are 0 through the point P, then all derivatives, all partials of order K are 0. Okay.
Right. Yeah.
Oh, this is what I said. Okay. Right. Okay, good. So we don't have much time. Yeah, now to finish, I just want to talk about the second derivative, because for us, the main, the main character in the course will be the second derivative, thanks to the Laplacian. So, right. So I want to just talk about the second derivative now. Okay. Okay. Yeah. So it's the second derivative. So if f is a C2 function, so then now we know that the second derivative is a symmetric bilinear function, right? But so it's a symmetric bilinear form. We know it can be identified with a symmetric matrix, right? Yeah. So this space sim2 v star, this means symmetric bilinear functions on V. Well, V is Rn. So this is the same as, this is isomorphic to symmetric matrices, right? Symmetric matrices. And how do we see that? So d squared f at P of V comma W, this will be the sum over Ij del squared f del xi del xj at P into Vi Wj, right? Yes. And this I can write as the inner product of a matrix, a symmetric matrix, HF at P into V, inner product with W, where this matrix HF at P is just what's usually called the Hessian matrix of F, del squared F, del xi, del xj at P, right?
Right.
Okay.
Yes. Yes.
So in this case, our second derivative, which is a symmetric bilinear function, it gets identified with a symmetric matrix. All right. So the second derivative can be identified with a self-adjoint linear map. Okay. That's the point. I mean, we don't have such identifications for the higher derivatives. Those are just multilinear maps. But for the second derivative, we have this isomorphism. Symmetric bilinear functions are the same as self-adjoint matrices. Okay, so the second derivative can be identified with a matrix called the Hessian matrix, which is del squared f del xi del xj. Okay. Now to finish, suppose f is a differentiable function from Rn to R, and suppose P is either a local maximum or a minimum of f, then if I look at f restricted to any straight line passing through P, then this will also have a local maximum or minimum at t equal to 0, this function f of P plus tv. And so therefore its derivative will be 0 since it's just a function of one variable now. So 0 will be equal to ddt at t equal to 0, f of P plus tv, that is dfp of V, right? So that means this is true for all V. So that means dfp will be identically 0. Okay. So all I'm saying is the usual, it's just the generalization to higher dimensions of the usual fact from one variable calculus. At a local maximum or minimum, the first derivative vanishes. All right. So this is true. DFP will be 0 as a linear map at any local maximum or minimum. Now, what about the second derivative test, right? So in calculus, we have the second derivative test. So what does that give us in higher dimensions? So suppose f is a C2 function from Rn to R, and then we can say the following. So if P is a local maximum of f, then the Hessian will be negative semi-definite. So HFP will be less than or equal to 0. Well, what does this mean? So HFP is a symmetric matrix. Symmetric matrix less than or equal to 0 means the corresponding quadratic form, inner product of HFP V comma V, this is less than or equal to 0 for all V. Okay. So at a local maximum, the Hessian is negative semi-definite. And we have a partial converse that if P is a point where the first derivative is 0 and the Hessian is strictly negative definite, then P is a local maximum. In fact, a strict local maximum. Okay. So yeah, so to finish, let's just quickly prove this. So one direction is very simple. If P is a local maximum, then along any straight line, F has a local maximum along any straight line. So you just differentiate twice along the straight line. You'll get 0 is greater than or equal to the second derivative along the straight line. Second derivative along the straight line is d squared f of v comma v, which is the same thing as inner product Hessian v comma v. Right? So the Hessian will be negative semi-definite. And conversely, if the Hessian is strictly negative definite, then restricted to the unit sphere, this quadratic form will be negative, right? It will be bounded away from 0. And then for h small, we use the Taylor theorem. F of p plus h will be fp plus, so the first derivative is 0, so the first order term vanishes. So the second order term will be 1 over 2 factorial hfp h comma h, and then there'll be little o of a norm h squared. And so this HFP of h comma h, this is less than a negative constant epsilon naught times norm h squared. And then you have little o of norm h squared. So if h is small enough, this negative term will beat this term. And so this will be strictly less than f of p. Okay. Is that all right?
Yes.
Okay. So we're out of time. So the next class will be Tuesday at 2 o'clock. Is that okay for everyone?
Yes, sir.
That's fine with
it's
me.
okay for me.
Rudrada, ঠিক আছে 2 o'clock? Okay, so all right. So then see you Tuesday at 2 o'clock. Okay.
Okay.
So I'll stop here.